number 5, which is mainly looking at the application of L'Hopital's rule, which you guys have seen this week. So the way I thought we should do this is I'll start with question 3, 4, 5, and 6, and then maybe circle back to question 1, because question 1 requires some manipulation that I think might seem a bit difficult at the beginning. So I think just to get us started, we should start with question 3, right? And then we'll move along. All right. So this question is asking us to apply L'Hopital's rule to solve these particular limits. And if you see if you can look at question 3, it has the limits as x is tending to infinity of ln x squared over over e to the 2x. Obviously here now we have ln is tending to positive infinity, because remember x cannot be negative when you have ln, right? So what happens when we substitute the value of infinity into this expression? We have, right, basically in the numerator we have infinity, right? So because you have ln of infinity, which will just give you infinity divided by e to the infinity, which is just infinity as well, right? So you have infinity over infinity, right? Which is an indeterminate form. Right? And then now that you see that you got the indeterminate form infinity over infinity, you can apply L'Hopital's rule, because remember, L'Hopital's rule is only applies to indeterminate forms in the form of infinity over infinity or 0 over 0, right? And in our case here, we have infinity over infinity. So how do we apply L'Hopital's rule to this? We have to first, right? Let's rewrite it. We have to take the derivative of the numerator, right, divided by the derivative of the denominator, and then just take the limit of that, right? So let's calculate the derivative of ln x squared, right? Now here, we basically have we're looking for the derivative of this whole thing here, which right, so let me just write the derivative as prime there. And basically we have the derivative of a function squared. And the way you do it is you take down this exponent, which is 2 in our case. Then you multiply it by the original function, which is ln x, right, to the exponent of whatever the original exponent was, minus 1, right? So here in our case, we have 2, so it's 2 minus 1, so it's to the exponent of 1, so we can just leave it like that. And then multiplied by the derivative of that function. So what's the derivative of ln x? I'm asking you guys.
It's 1 over x.
Okay, right? So the derivative of ln x is 1 over x. So you just multiply by 1 over x. And to make it simple, the 1 will just multiply n, so we can just take it out, right? So this is our derivative of the numerator. Now let's look at the denominator. Our denominator is e to the 2x, right? The derivative of e to the 2x, again, you have some function. Now, this is a exponential function. And the way you do it with exponential function is first you write it back, okay? So its derivative is, let me just write the derivative sign here. So the derivative of that is just first you write back the function when you have an exponential, then you multiply by the derivative of what is in the exponent. So in our case, we have 2x, and the derivative of 2x is what?
2.
2, right? Thank you. So the derivative of 2x is 2, and then multiplied by, usually, right, is multiplied by ln of whatever the base is. So in our case, it's ln e, but you know that ln e is just 1. So we leave it out, right? Because you guys remember that the formula, so let me just give you the general formula that I'm sure you guys are familiar with. So if you have some function like a is a constant here, to the exponent of f of x is just a function in x, and you're trying to find the derivative of that, right? It's equal to, again, you rewrite first the expression, meaning a to the f of x, multiplied by the derivative of the exponent, which in our case is f of x, right? And then multiplied by ln of ln of a, right? So this is the general formula for an exponential. Now, a can be anything, but in our case, a just so happens to be e. So when you substitute ln of e here, it's 1, right? You guys remember that from your exponential functions identities, right? So now that we've done with that, we just rewrite our original limits and we write the derivative. So we say, after applying L'Hopital's rule, we get, now in the numerator, the derivative of ln x squared, we found it to be what? Found it to be 2 ln x over x. So let's copy that and put it in our numerator here. And then in the denominator, the derivative of e to the x is e to the 2x, sorry, is just e to the 2x over multiplied by 2. Copy that there. Immediately, you can see that when you simplify, right? So let's simplify this. You have that the 2 in the numerator and the 2 in the denominator will cancel, right? So you can take them out. Also, you have that the x that is right here will just go down here, right? Because remember, you're dividing two fractions. And when you divide two fractions, you take the first fraction multiplied by the inverse of the second, right? So you guys know how to do this. So this will just become ln x now divided by x e to the x e to the 2x, right? And again, when we substitute in the value of x here, we have again infinity in the numerator divided by infinity in the denominator, okay? Which is giving us the indeterminate form again, right? So it's giving us that again, which is indeterminate, right? So we apply L'Hopital's rule again, right? So after applying L'Hopital's rule again, we get, I'll just copy this and then we'll change it. So what's the derivative of the numerator? What's the derivative of our numerator here? That's your guys' job now. Tell me. What's the derivative of ln x?
1 over x.
Exactly, right? So the derivative of ln x in our case is 1 over x. And here, for the denominator now, we will use the product rule. Okay, we will use the product rule. Because we have the denominator of x multiplied, the derivative of x multiplied by e to the 2x, right? And here, we use the rule that tells us when you're trying to find the derivative of a times b, a and b can be any function, or let's just write them as two functions. F of x multiplied by g of x, and you're trying to find the derivative of that, what you do is you find the derivative of the first function, and then you multiply that by the second function plus the derivative of the second function multiplied by the first function. Okay, so that's the identity. Again, you guys should know this. Now, knowing this, you just apply the formula here. So tell me, guys, try to apply this formula to this derivative here and tell me what you get. I want you guys to attempt it now. I'll give you 5 minutes. Attempt the question. We're trying to find the derivative of x times e to the 2x by applying this identity here, the product rule for derivatives. So tell me what you get.
would it be 3e exponent to x?
Sorry, 3. Where does the 3 come from? Just attempt it. Use this formula here, right? So the formula is telling you when you have the product of two functions, you take the derivative of the first one. So the derivative of x multiplied by e to the 2x, right? Plus the derivative of e to the 2x multiplied by x. Okay, that's the product rule. So just apply that and tell me what you get. Does anyone have it? Even an attempt, guys, just anything.
It's e to the power 2x plus e to the power 2x times 2 times x.
Right, plus e to the power 2x times 2 times x. Right. Okay. Does everyone understand how we got this?
No, sir.
Right. So the way we did it was we took we just used this identity here. The derivative of f of x. Our f of x is x here. What's the derivative of x? Of x, it's 1, right? 1 multiplied by g of x, and our g of x is just e to the 2x. So 1 times e to the 2x, which is just e to the 2x. And then plus the derivative of g of x, right? Which is the derivative of e to the 2x, which is 2, right? Multiplied by the same function, e to the 2x, right? And then all of that is multiplied by f of x, which is just x, right? So we have 2x times e to the 2x. Does that make sense now?
Yeah.
Yeah. So that's it. So you just had really, these things are not very very complicated, but they take time. So you need to sort of practice in your own, so you can in your own time, so you can be able to solve these problems quite quickly. Okay, so let's just plug in this derivative that we found here into the denominator there. And what we get is now this, which of course can be simplified, right? Can be simplified to be equal to, just copy this. The x can come to the denominator. So 1 stays up there, and we have the x come here, right? And then when you substitute in the value of infinity now, what do you get? Tell me, what do you get? I want you guys to attempt it and let me know what you get. Plug in the value of x, which is infinity, positive infinity, and then into this, and tell me what you get. Do we get a definitive answer or still an indeterminate form? Sorry, go ahead. Hello, I thought I heard someone. Anyone with the answer?
Isn't it 0, sir?
Yes. Does everyone understand how we got 0?
Please.
If you don't understand, don't hesitate. Just you can unmute yourself and speak up, and then we can discuss it. I hope everyone understands. Okay. Right, let's move on. You can always stop me at any time. So we found 0. So now we can conclude that the limit of our original function, right, is therefore equal to 0. This is after applying L'Hopital's rule twice, okay? And that's it. So now, let's do the same thing for question 2. Now, quickly, I want you guys to plug in the value of x there and tell me what do you get into question 4. What do you get?
It's infinity over infinity.
Right. So you get infinity over infinity, which is again an indeterminate form. Right? It's an indeterminate form, and therefore we have to apply L'Hopital's rule, right? So now let's copy this and apply L'Hopital's rule. So after applying L'Hopital's rule, we get, what's the derivative of the numerator here? I want you guys to attempt it. What's the derivative of the numerator here? Just so it's good practice for you guys. And for this particular case, we'll be using, especially for the exponent one, we'll be using this identity here. Okay, so just keep it in mind as you're calculating. So what do you get for the numerator? Guys, attempt it. I'll give you 5 minutes, and then let me know what you get. Anyone with an answer?
It would be 3 plus 2 then 2.
Okay, 3 plus 2 ln 2. And does everyone agree here? Look at the original function.
Two. Say
3 plus 2 exponent
it
x.
is 3.
3 plus, say that again, to the x. Is that it?
It's 3 plus 2 exponent x, and then it's ln, right?
Oh, ln 2.
Yes.
Does everyone agree here? Okay. Right. Sorry, go ahead. Go ahead.
I'm lost.
You lost. Okay. So what we did was we're trying to find the derivative of this numerator here, right, in the original function, because we're applying L'Hopital's rule. So the derivative of 3x, right, is just 3. Okay, so that part I'm sure you get. Now the derivative of 2 to the x, I said we would apply this formula here. You have some function that is like a to the f of x. When you're trying to find the derivative of that, you just rewrite the function, and then you take the derivative of f of x, and then you multiply by ln of a, right? So now in our case, a is equal to 2. So we'll have ln of 2. You get that there, right? And f of x is equal to x. So we'll get 2 to the x, which is our 2 to the x here, multiplied by ln of a, which is our ln of 2 here, multiplied by the derivative of f of x, which is x, right? What's the derivative of x? It's 1, right? And then when 1 multiplies all of this, it just stays 2 to the x times ln of 2. Does that make sense now?
Yes.
Okay. So now attempt the same thing for the denominator and tell me what's the final answer.
Two plus 3 exponent x ln 3.
2 plus 3 exponent x ln 3. Right? So you guys are getting it. So that's good. And so now, when you substitute in the value of infinity, what do you get? Yeah.
I think it's still infinity of infinity, sir.
Yes. So you still get infinity over infinity. So now what you do is you have to apply L'Hopital's rule again, right? So we repeat the same thing. After applying L'Hopital's rule again, you guys can already start calculating the derivatives of the numerators and denominators and tell me what you get. So let's copy this and tell me what we get for the numerator here and the denominator when you find the derivative. Anyone with the answer? What do you get in the numerator?
It's 3 exponent x ln 3.
Sorry, in the numerator. Yeah. You're trying to find the derivative of the numerator, right? So what do you get here?
It's 2 exponent x ln 2.
2 exponents x ln 2. Okay, does everyone agree? Let me write it and let's see if it makes sense. 2 exponents x ln 2. Does everyone agree here? Guys, what do you think is the answer for the numerator here, 2x ln 2? Is it right? I'm asking you because I want to see if you are attempting the question itself. Is it right or is it wrong? Is there something missing or not? Because think about it. Sorry, go ahead. Think about it here. We have 3 plus 2x ln 2. So when you find the derivative of 3, it's 0. Okay, so it's 0. Plus the derivative of 2x ln x. Now remember that ln 2 is a constant here. Okay, so you can just keep it to the side and find the derivative of 2 to the x. But we already established that the derivative of 2 to the x is 2x ln 2. So you will have 2x ln 2, right, multiplied by the other ln 2 that was there originally, right? So you will have, okay, I'm hoping this makes sense. You have 2x ln 2 squared here, because you will have two 2x ln 2s now, not just one. Because you already had 1 now, but then when you find the denominator, the derivative of 2 to the x, another ln 2 comes in, and then it multiplies with this other one, it becomes ln 2 squared now. Does that make sense?
Yes, it does.
Okay, so now repeat the same thing for the denominator and tell me what you get.
Wouldn't it
It's
be
3 to the
3?
exponent x.
Sorry, go ahead.
It's 3 to the exponent x ln 3 squared.
Exactly, right? So 3 to the exponent x ln 3 squared. Okay, so now what happens when you apply sorry, just give me a minute. right? So what happens when you apply infinity into this expression? What do you get?
Is it still infinity over infinity?
Okay, so now we're getting to a point that you guys will have to pay attention to. So as you can see here, we will have 2 to the x in the numerator and 3 to the x in the numerator. But now think about it. As x is tending to infinity, will the numerator be bigger than the denominator or smaller than the denominator?
The numerator will be smaller than the denominator. Possible.
Right? So smaller than the denominator. So you can clearly see as you go higher and higher in values of x, 2 to the x will be smaller than 3 to the x. Okay, we can leave out the ln 2 squared and the ln 3 squared first. We're just looking at the terms in x. So 2 to the x will be smaller than 3 to the x. So now when you go higher and higher, you can immediately already tell that the numerator will be smaller than the denominator. And you know, with exponent functions, the difference as you go higher and higher with values of x, the difference between 2 to the x and 3 to the x is getting larger and larger. So at some point, 2 to the x will be a very small number compared to 3 to the x, right? And at that point, you can already see, remember what we said when we were looking at limits initially, we said you can already see that 2 to the x will be small and 3 to the x will be large. So what happens when you divide a small number with a large number? What happens?
Limit approaches 0.
Right. So the limit approaches 0. So that is what you do. You can do in this case, because as you can notice, if we keep applying L'Hopital's rule, you will see that you will keep getting the exponent that comes back, right? That we'll keep getting 2 to the x times ln 2 to 3 and then 4, same thing in the denominator. So we'll keep having the 3 to the x and the 2 to the x. But we can use a sort of trick to tell us where the limit is tending to, because we know if we sketch these two functions, 2 to the x and 3 to the x, we can clearly see how big of a gap there is between the two graphs, right, of these two functions as x is tending to higher and higher values. Okay, so that is what we will do here. And technically, right, we could have done it as well for this one, right, for this question 3 here. But the problem is you need to first show that you applied L'Hopital's rule multiple times. But you could already sort of tell that as you apply higher and higher values of x, right, ln of x, if you plot the graph of ln of x and you plot the graph of e to the 2x, e to the 2x will be significantly higher than ln x, right? So as you go higher and higher in values of x, you'll see that ln of x will be significantly smaller than e to the 2x, right? Which tells you that the limit then, right, will be sort of like a small number divided by a large number again, which should give you 0, right? Which comes back to the solution that we found here. Okay, so that is sort of the trick that you will be using in this case. And does it make sense? Does everyone understand?
Yes.
All right, thank you so much. Just give me a minute. Okay, guys, let's do it. So I'm assuming everyone understood that. Let's move on to sub question 5. So now for sub question 5, we have the limits as x tends to 0 of x10 x over sine 3x. So substitute the value of x here and tell me what you get.
It's undefined.
What sort of undefined form does it get?
I think the denominator becomes 0.
And the numerator?
It's also 0.
Right, so you have the indeterminate form. So now you have to apply L'Hopital's rule. So again, we write, after applying L'Hopital's rule, what do we get? Now you can start to quickly find what's the derivative of x10 x and what's the derivative of sine x. So just attempt that and tell me what's the derivative of x times 10 of x. Again, here you can clearly see that you have two functions, x and 10 of x. So you should use what rule? We've used it before. What rule should you use here?
Product rule.
Product rule. So try that and then tell me what you get. Anyone with the solution?
Isn't it tan x plus secant squared x times x?
Let me write it. You said tan x plus secant squared of x, like this. I'm hoping. Do you guys agree?
Yeah.
Okay. What about the denominator?
I
What
think
do you
it's
get?
cos 3x.
Okay, let me write it down and see if you guys agree. Do you guys agree?
Yes, sir.
Are you sure? Have a look at it again. Is the derivative of sine of 3x equal to cos of 3x?
It is 3 cos 3x.
Yes, right. Because you are applying the chain rule. Remember, the chain rule tells you go from outside to inside, right? So you can go the sine of 3x, the derivative of that is the cos of 3x, but then multiplied by the derivative of the 3x that is inside, which is just 3. So 3 cos 3x. Okay, so pay attention to that. Now, what happens when you substitute the value of 0 here? What do you get?
Zero over 3.
It's 0. It's 0.
So you get 0 over 3, which is equal to 0, right? So immediately here you get 0, which is a valid answer. So you don't have to apply L'Hopital's rule again. Okay, does anyone understand how we got 0 here? If you don't, feel free to ask the question. Okay, so I don't see any questions, so I'll just move on to this. So here we have, now this one might be a bit challenging, so you have to go back to what you guys did for the derivative of inverse trigonometric functions. So what happens when the limit of x is tending to 0 of sine inverse of 4x over tan inverse of 5x? So what do you get when you substitute this? Guys, what do you get? So basically, this is what you're trying to solve. So what do you get when you have that? What's the sine inverse of 0?
Undefined.
What
so.
undefined form? What's indeterminate form? you get?
0/0.
0/0. Does everyone understand how we got 0/0? All right.
Yes.
Okay, so now, again, we apply L'Hopital's rule. So after applying L'Hopital's rule, what do we get here? You guys can already start looking for the derivative of sine inverse of 4x, right? And maybe it might be useful to first remember the formula. What's the derivative of sine inverse of some function f of x? I remember, if I'm not mistaken, these formulas are in your textbook at some page, so you have to sort of remember them. So what's the derivative of sine inverse of some function f of x? And then you need to figure out the same thing for tan inverse. So apply the same logic to tan inverse. Tell me what it is. And then we can plug in the values that we're trying to get here for our problem. Anyone? Okay, so I'll give you the formula, but you guys should sort of go back to it in your notes and figure out how this makes sense. So there's the derivative of sine inverse of f of x is just f of x prime, so the derivative of the function f of x divided by 1 minus f of x squared, right? All to the exponent of all to the square roots, which is the same as the exponent of 1/2, right? So you could write this as right, and then for 10 you have almost the same thing, but now in the denominator you have 1 plus f of x squared, right? So these are the formulas for the derivative of sine inverse and tan inverse functions, right? So you should know them. Now, if you apply them to our problem here, what do you get? Now, I want you guys to apply it to the problem and tell me what you get in the numerator. Come on, guys, you can do it. I know you can. I've given you the formula. All you have to do is apply that to the numerator and tell me what you get. What do you get? Guys, come on. What do you get in the numerator? Cosine inverse of 4x.
Minus 16x squared.
Sorry, go ahead.
4 divided by the root 16x squared.
4 divided by the root of 69 squared.
4 divided by the root 1 minus 16x squared.
Oh, okay, sorry. I didn't hear correctly. Okay. So 4 divided by the root of 1 minus 16x squared. Now apply the same logic to, does everyone agree first? Okay, no one is saying anything, so I'm assuming you agree. Apply the same logic now to the denominator. What do you get in the denominator?
5 over 1.
5 over.
Sorry, 5 over?
The root of 1 minus 25x squared.
1 minus, are you sure?
Oh, 1 plus 25x squared.
Yeah. So there you go. And then let's simplify this expression. What do we get when we try to simplify this whole thing here so it looks a bit nicer? You get so you have 4 multiplied by 1 plus 25x squared divided by 5 multiplied by the square root of 1 minus 16x squared. Right? Now, can anyone tell me what happens when you substitute in the value of x here? What do you get?
You get 4 over 5.
Thank you. So does everyone understand how we got 4 over 5?
Yes, sir.
Please mute yourself. Sorry? Yeah, okay. If you're not speaking, thank you. So Okay, I'm assuming you guys get that. Now, let's apply it to the next set of problems. So since time is moving, this is what I suggest. I want you guys to attempt question 1 and 2, right? Based on everything that we did here for all questions 3, 4, 5, and 6. And based on what we'll be doing for the first question here, 7, right? Because basically you have to apply the same sort of logic. So now for these type of questions, we asked to evaluate the limits. As you can see, what happens when you substitute the value of x in this? What do you get? What do you get, guys? Come on, this is a simple sort of exercise. What do you get?
0.
You don't just get 0, you get 0 to the 0, 0 to the exponent of 0 to the exponent of 0, okay? Which is undefined, right? So now you have to apply L'Hopital's rule in some way, but you can't apply L'Hopital's rule when you have 0 to the exponent of 0 to the exponent of 0. Okay, so you only apply, remember, L'Hopital's rule when you have infinity over infinity, or you have 0 over 0. So now let's try to see if we can manipulate this expression here to have 0 over 0 or infinity over infinity, and then apply L'Hopital's rule. And to do this, we'll be reminded that we've been reminded that we have this rule that when you have e to ln x, that is just equivalent to x. Okay, so now if we apply this rule here, this identity, to our problem, what we get is, okay, we get the limit of now e to the exponent of ln x to the x to the x, right? Which is equal to, do you guys understand this? So this applies for ln to the x, sorry, e to the ln x or e to any function. So f of x, let's write it in general. E to ln of any function, f of x. This applies, okay? So now in our case, f of x, which is our function, is just x to the x to the x, right? So does everyone understand this so far? Hello? Does everyone understand? Can I move on? Okay, I'll just move on.
Please go over it one more time.
So we have this identity from our exponential function. We have the fact that for any function f of x, e to the ln of x, e to the ln of f of x is just equal to f of x. Okay, so this is an identity of exponential functions that you guys should be familiar with as well. Okay, so now from this identity, all I did is I just substituted f of x in this identity by x to the x to the x, right? And then we get e to the ln of x to the x to the x. Does that make sense now?
Yes, sir.
Now remember, here, it might seem a bit complicated, but what you have is x to the exponent of x to the x. So basically, since you have ln there, you can take the exponents out, okay? So by taking the exponents out of the ln function, you have x to the x that comes out here, right? Which is multiplied by ln x now. Okay, I'm hoping this makes sense as well. So now you have, what you have is e to the ln x, sorry, you have limits as x tends to 0 from the positive side of e to the x times ln x. And again, remember, here, you can basically break it down. Okay, you can break it down, or rather, okay, you can just bring in the limit sign. Okay, so this can be equal now to the limit, right? E to the limit, or as x tends to positive to 0 from the positive side of just x to the x times ln x. Okay, so this is an identity that you guys are familiar with. You can just take the limits into the exponent, okay? When you have an exponent function like this. So, and then now you're trying to find the limits, right? So trying to find the limits of e of x as it tends to 0 from the positive side of x to the x times ln x. So let's just solve it separately. And then as soon as we find the answer, we'll just plug it back into the original function. So this is what you're trying to do. Again, you can clearly see that just give me a minute. Okay, so you can clearly see that you have the limit of a function multiplied by another function, which you can simplify again. You can break up into two parts. So the limit of these two can be equal to just the limit of the first one, right? Of the first function in brackets multiplied by the limit of the second function, which is ln of x. Okay, so this is again a property of limits, right? So you guys should be aware of this. And then now we're trying to find, let's find the limit of x to the x, because remember here we're getting, let's solve this separately as well. I'm trying to break it down into steps so you guys understand. The limit of x to the x as x tends to positive infinity. Again, if you substitute in, you'll get 0 to the 0. And then you'll use again this identity here, right? So you get e to the ln of x to the x right? And once again, the x exponent can come out. So then you get, right? you can take this exponent x out and put it out here, and you have limits as x tends to 0 from the positive side of e to the x ln. And once again, you can take the limit inside the exponent, right? So you can take this, but now you take this limit in there. Okay. And now you're trying to find the limits as x tends to 0 from the positive side of x ln x, which is just, again, if you substitute the value of x, you'll find it 0 times the ln of 0 from the positive side. And the ln of 0 from the positive side is minus infinity, right? So you can just, again, you can manipulate this, right? I know it's a bit long, but it's for your interest, so you need to understand this, which is just can manipulate this as e to the limit as x tends to positive infinity of x divided by 1 over ln x, because these are basically the, oh, sorry. Right? And then when you substitute the value of x, what you get is 0 over 1 over ln of 0, as 0 tends to, as x tends to 0 from the positive side, which is negative infinity. So you have basically 0 over 1 over infinity, which is 0. So 0 over 0. You can apply L'Hopital's rule here, okay? And as soon as you apply L'Hopital's rule here, right, to solve this limit here in the exponent, if you do it multiple times, right, you will end up getting that this limit is equal to 0. So I'll leave you to solve that. But you should get, right, you should basically get that this limit in the exponent here, right, is equal to 0. So that's what you should get. You should get 0 there after you apply L'Hopital's rule. And this should give you e to the 0, which is 1. So you would have found that this limit is equal to 1. Now, when you multiply it into this, our original expression here, you have 1, right, times the limit of ln x as x tends to 0 from the positive side, which is negative infinity. So you have 1 multiplied by infinity, right? And of course, this will just give you 1 multiplied by negative infinity is just negative infinity, right? Let me just find infinity, copy it. So 1 times negative infinity is just negative infinity. And immediately you can plug in this expression into the solution into the original expression that you had here, which is just e to the negative infinity. And what is e to the negative infinity? Guys, are you still here?
No, you're not.
Just tell me, what is e to the negative infinity? Right? As you can see, it's just basically the same as 1 divided by e to the infinity. Right? And what is 1 divided by e to the infinity?
Zero.
0. So our final answer should be 0. So this one might seem a bit complicated, but what I would suggest is, since we're running out of time, take a screenshot of this and then just go back to it and attempt it. Okay, so take a screenshot of that, or you don't even have to do that. I'll be providing you with this, so I'll be keeping this session for you guys, and then you can just go back to this and attempt it on your own. But basically what you did here is similar to what you would be doing for 8 and 9. Okay. And then going back to question 1 and 2, you'll be applying the same logic again, just to apply L'Hopital's rule. Okay. Right. So that is it.